Hi, everyone. Thanks for having me. So I'm super excited to be here in virtually. So today I'm going to talk about this initiative, FRIDA. So FRIDA stands for Framework and Robotics Initiative for Developing Arts. So as you can see in this video, this is about robots that can paint. So, okay. So before I start, I need to introduce the whole team. So this is the largest team that I ever had for an unfunded project. So especially I need to mention Peter. So Peter is my PhD student who has been leading this project, mentoring a lot of younger students. And then there are more students joining for the 3D part of the FRIDA project. And also Jim McCann is also kind of leading together with me. Okay, so let me start with like what the goal of the FRIDA project is. So when we talk about robot painting, many people think that we are going to take over the artist's job and, you know, this like AI being creative on its own, but it's quite the opposite. So what we are aiming at is to help human creativity using these robotics technologies. And also at the same time, we call this project as a playground for roboticists. So it promotes a lot of different areas of robotics research that also involves a lot of like large collaboration. Okay, so when we look at this robot kind of doing the painting, given a like a known artwork. So as I mentioned, this is not to create another like intelligent system that can be creative on its own for its own like purpose, but it's mostly for helping people. So especially people like me. So when I was young, I wanted to be an artist, but I wasn't born with the right set of skills. So now I'm very excited to have this FRIDA that I can work with. So I can come up with an idea that I want to express about what's going on around the world, for instance, and then I work with the FRIDA to actually get it into a painting. So to stress that again, we designed FRIDA to paint what we humans want to paint using different modalities. So we want to make intuitive interface for humans to interact with FRIDA. So we want to support natural language communication and also something like sample images, because sometimes it's hard to describe using language or like complex shapes, but you can show a picture of a certain scene or objects. Recently, we also started using sound as an input. So when FRIDA is painting, if we play a sound of rain, then the background turns into kind of rainy scene and so on. So there could be gestures and other things that people want to use to express themselves, to communicate with our system. Okay, so it's kind of continuing that story. So what we are aiming at is human-robot collaboration rather than AI just creating something on its own. So many people are familiar with that, some systems like DALL-E, and the results are impressive. And DALL-E is the image qualities produced by DALL-E or Stable Diffusion, they look amazing, but there's less of a control that's given to a human users. So people have come up with an idea for like prompt engineering or some manual work to work better with systems like DALL-E. So I'll use an example to illustrate this. So these are kind of prompts that I care about. So for Roe versus Wade or women's rights to choose. And these are the images I can get using DALL-E. So again, images look very photorealistic and high fidelity compared to previous existing works, but the contents are not something that I can resonate with. So with FRIDA, I can express what I'm thinking about what's going on around the world with a maybe more expressive or richer voice. So again, FRIDA is for human-robot collaboration. Okay. And then on the robotics research side, there's just tons of different areas to address. So many challenges come from the computer vision side, perception, because painting requires the system to constantly observe what's going on the canvas. So perception system, and also learning and control. So right now, this part is something that we are not really doing a lot of work, but we want to do it in the future. But there is a lot of robot control that we can do better than what we have currently. So as you can see right now, the FRIDA doesn't have a hand, so the brush is just attached by a tape. So so learning and control is obviously the thing that we can do. And planning is the majority of the current research is focused on. So because painting is essentially a planning problem. So we start with an initial state, which is an empty canvas. And then the system takes a sequence of brush actions to move towards the goal state, which is the final canvas. So by doing this planning work, we have to deal with this sim to real gap, which is one of the major issues that we are facing right now. So later in the talk, I will talk more about this part. And then, as I mentioned, in order to support multiple modality inputs to communicate with the human so that people can really express what they want to paint so that the end outcome really matches with their high-level semantic goals. And then there are a lot more, but I'd like to touch upon some topics on responsible AI, because we are generating contents that includes some messages. So we'd like the system to be a little bit more aware about its responsibility. And also eventually, if we give the full control back to the human users, humans are going to be more responsible together with the AI system. So these are kind of some sample topics that we can study using this type of art related work. Okay. And then for this next, I will kind of show you what has been done in this robotic painting world. So again, many people are familiar with very up-to-date text-to-image synthesis systems. And again, the results are really amazing. I'm like very, very impressed. But the big problem for us is because we want the robot to be able to paint. So these algorithms are useful. So we actually use some of these too, but essentially these are virtual generations. So the whole image is generated at once rather than a sequence of actions. So these outcomes can be printed, but it cannot be painted as is. So someone has to turn that into a painting actions. And then, in fact, there are stroke-based rendering, like planning-based approaches. So some of the earlier work by Aaron Hertzman, and also includes some of our own work, which was kind of combining text and style image together. But these approaches have a very primitive brush strokes. So the brush strokes are so unrealistic. If you just use it for the robot actions, it doesn't really produce outputs that are recognizable. So, okay. So for brush modeling, there's tons of existing work in the field of graphics. And these are really high fidelity, high quality simulation environments. So one example here, this GAN-based one, it takes really a lot of training data to train this model that produces very, very high fidelity brush stroke simulation. And also this DPG, which we also have tried before. The outcome looks really good in simulation. But again, the problem is it's not designed for the real system. So it's just unknown. So no one can actually really try how well this works on the real robot. Okay. And then more recent work. So this paper was published in IROS a few months ago. And this one is using the real robot, but they paint, they're not really painting, they're drawing on an iPad. So they also address a little bit of a sim to real gap, but to me, I want to kind of put their work in between real and simulation. And these are some of their results. And then there's another very recent work, Dream Painter, and they really closed the gap between simulation and real environment by not by changing the real robot like environment, but they simplify the sim. So the gap is smaller, but end outcome would also be very simple. So all of their pen drawings look something like this. So it's kind of a sketch drawing, or so pen drawing, but the fidelity is now like not supported. So these are some of the existing work. And then there is a really, really high-end robotic system that can do a very, very nice paintings. And these are commercial products, so they sell them at a very high price. And these factory, dark factory portraits, and also E. David that came out a few years ago, they produce really amazing work. But as you can imagine, these are highly engineered systems, so these are not really generalizable solutions. So what we are aiming here is to come up with a generalizable approach that can produce real high quality painting. Okay, so let's look at the FRIDA project. So some of the early work we started was during pandemic. So we used this small, like low-end robot to paint. And that's when we saw this paper using reinforcement learning to generate the very good output in simulation. So in their simulation outputs, it's almost the same as the input image. So we were also wondering, like, what's the purpose of having this painting? Because it looks almost exactly like the input. So it's like very complicated way of printing an input image. So but then when we tried this with the real robot, what we learned was their brush stroke models were unrealistic. So for instance, some of the early strokes in the stage are very, very large. So almost half the size of the canvas is one brush stroke. And so those are really not supported by the real real brushes. So when we tried, this was what we got. So in this early work, what we did was, instead of fixing it in the real side, so it is, our idea is a little bit similar to that dream painter. So we simplified the simulation environment. So we added some constraints, so it doesn't allow using those like gigantic size brush strokes, and turn all the brush strokes to a reasonable size and length. That way the end output was a little bit improved, but still there is a huge gap between simulation and real environment. Okay, so that's how we came up with this closed loop approach idea. So for us, painting starts with the high level intention. So the goal, so I also interviewed many artists, how they come up with the idea for their final painting. And very few painters actually had a very concrete vision for what they're going to paint. So a lot of people say, like they start with somewhat vague idea, but they know what they want. So it's a little bit subtle concept, but there is a high level semantic goal that they want to accomplish, but that's only like being realized through painting process. So it is a very iterative process. So we designed our architecture to follow that model. So we start with the very high level concepts. So the input for the painting can be described in an abstract way using language or sketch. And then the planner kind of starts generating the plan and then take brush actions. And there is a visual feedback that from the camera observation that puts the feedback into the loop, and then it reconsiders the high level goal given the current canvas, and then replans. So it keeps replanning using the visual feedback, and then try to optimize for that high level goal. So the painting continuously evolves until it's done in the final stage. Okay, and then so in order to do so, what we need to have is this imagination component, which is the simulation. So instead of kind of trying out all the strokes on a real canvas, in simulation it tries out ideas in order to make this brush stroke as realistic as possible, we use this real data to refine the simulation environment. So the idea was also used in other robotics problems. So the name for this is real to sim to real, because the simulation was modified using the real data. Okay, so these the FRIDA architecture and the framework includes many pieces, but today I'm going to focus on the two aspects. So the first one is this how to reduce the sim to real gap. Okay. So this is a little bit of a detail how we model the brush stroke. So right now it's modeled using only 3 parameters. So like the length and the bend and how much this height is the force, like estimated force, how hard the brushes should be pressed down. So it also controlled a little bit of a thickness too. Okay. So the simulation environment basically needs to take these arguments, input arguments, and then generate the brush stroke in pixel space. So the naive approach could be similar to existing approach, like take a lot of training data and then generate. And the proposed idea was using the differentiable operations, because one of the key idea was we changed the simulation environment so that everything is differentiable, so that we can use other differentiable operations to kind of do the transformation, and also for the training data, we can do data augmentation as well. Okay. So this kind of sketches how it is done. So using those 3 parameters, it generate the initial brush stroke shape. And these are some of the examples that were used to train this parameter stroke. And then just put it on the canvas, and then use the rotation and rigid transform to put it in the right location, and then colorize. So, okay. And then these are some of the results. So the first part just shows what the variance is for for each of these kind of parameters. And now that we can model the shape in a continuous way, the generated brush strokes in simulation look much more high fidelity. So this is a comparison. So the DIP-VG was the previous model that we also used. And you can see this is a training time and this is test time. But in both cases, you can see the shape look completely symmetric, and there's no noise, because this is more or less a discretized space. And then if you look at the FRIDA simulation, it really matches well with the real examples. So, and this the numbers show the quantitative part to measure the difference in L1 loss. Okay, just check. Yeah, I think I'm already kind of out of time, but quickly show the results. So this was the previous existing work, and then this was our earlier work using simplified sim environment. There was a little bit of improvement, and then the proposed approach. You can see the simulation quality is almost same as the perfect simulation, and then the final output is also very close to what was simulated. So it is a huge improvement. So this is a paper under review right now. And then for this multimodal part, which is how to interact with the user, I'm going to kind of show you some of the results. So for the feature space, this is another kind of experiment we did. So if we use just L2 loss, then this is a good example to say this is Pittsburgh. And if you just use L2 loss, if you look at the 2 pictures from far away, the color match much better because it is directly matching pixel by pixel. But this side is what we use because, again, our goal is to really satisfy the high-level goal. So this input image, even if it's a photograph that was given, it is an input that's supposed to be used as a reference. So we kind of add a little bit of creativity by looking at like rearrange these features in a feature space loss. So all the kind of features are a little bit more exaggerated in a way. So in this example, you can see using feature space loss, you can see a little bit more details, and especially in this cloud space, and also the grass shapes. Okay, and on this part, we did a little bit of a user study too. evaluate. So one of the key challenges on working on generative models is there is no good metric to quantitatively evaluate the performance. So we always accompany user study. So this is another area that we are looking into, how to propose a better metric that matches well with the human evaluation. So anyway, so in this result, a lot of users agree that the feature space loss version looked better. Okay. And then for the input modalities that we are supporting, we support style, image, and text. So this is a painting of a Harvey milk with this Oscar Kokoschka style. And then this another one is the Vincent van Gogh style, and another kind of prompt, which was a portrait of a robot artist in these two different styles. And then in this case, we also provide a sketch to give a little bit of information on the composition. So roughly this composition, but using this type of color texture. And then the contents are the two soldiers from two different countries dancing. So this is the produced output. Okay. And then do I have like a couple more minutes, or should I stop?
Yeah, sure. Couple minutes should be fine.
Okay, so yeah, thank you. So there's a tons of challenges and future directions we can go from here. So I list all the challenges. I can talk about this for hours, but today I'd like to kind of point out to the data bias part. So the other slides that I will share will look a little bit different from the raw painting, but it's addressing the data bias. So. Okay, so this is a question. So look at these images and see which one looks American. So we actually asked these to 336 people, and then they found that they both look American. And the model that was used to generate these images, the first row is using the stable diffusion, which is one of the top performer in text to image generation model, as is. And then the second one is we developed a culture aware stable diffusion, and this one was primed for American culture. And the two apparently there's no significant difference. So that indicates, I mean, we knew about it, but it kind of confirms that the data that was used to train stable diffusion, which contains 2.3 billion image text pair, is mostly American. Right. So what we did was we wanted to kind of be able to generate images for all these different cultures. So this is a workshop paper we just submitted. So on this work, we just showcased 6 different cultures. And for the same prompt, this is for Korea, this is for Nigeria, China, Grenada, and Japan. So the results compared to the baseline, we did a mini kind of user study, and people find it's less offensive and also less stereotypical, and also they are more relevant to their culture. So some of the images using just the baseline. So the baseline is a stable diffusion, and then we just put the name of the culture at the end as part of prompt. So the 2 people dressed in traditional clothing in Korea, for instance. And then so in Korea example, Korean people can recognize these are not Korean costume, it's Japanese, or they look more like a Japanese, maybe it's not even Japanese. In Nigeria, family eating together, they're all sitting on the floor, like dirt floor, and the people in Nigeria feel like this is like from 50 years ago. And then also Chinese people felt a little bit offended, like find these images very stereotypical and offensive. So the changes images are more relevant and more modernized. So all these examples we found, except for America, all the other countries are portrayed as like old cities. Okay, so this is a kind of new project that we are starting. So it's called David. So we are kind of fighting against these models that were trained with a lot more data than what we have. So this David is a diverse image data set that contains very, very small data to use for priming. So priming is the idea to really influence the output the way towards the target culture or target goals. So we currently have 6 countries and 6 types. So right now the culture is not like a one-on-one match for country, but right now that is the definition. But we want to grow this data set to include all the countries in the world, and then be able to control the bias as needed basis. Okay. And then this is another teaser. So since we had a lot of fun in painting, we also want to do the 3D sculpting. So, okay. So yeah, sorry I went over time. Anyone has questions, be happy to answer.
I think we can take 1 or 2 questions. So, yeah, I have one question. So, do you think like artists also use your system circles to be one or people like example artists actually?
Sorry, I couldn't hear the question clearly.
So, is there like ways for how do you think artists can use your system?
Yes, is the question whether artists can use our system?
Yeah, I think they can use it, but what kind of like synergy or effect you think does they have like creativity, and if they are able to use your system, what kind of like effect might have?
So like for the real artist, this could be kind of the like a helper. So if they need to paint a lot of similar sequences, maybe FRIDA can be used to like paint the next frames as a helper. But for people more like a non-artist, but art, we call them art enthusiasts. So they love arts, but they don't have skills. So I'm a perfect example. So we can work with FRIDA so that the output is produced. And then also, we don't have like interleaved system, but it is a direct extension of what we currently have. So the FRIDA can always take existing canvas as an initial state. So it doesn't have to be an empty canvas. So maybe you started something and then have FRIDA finish, or the other way around. So
Great, thank you. Any other questions?
Thank you for your talk. Jenny. Have there been studies that show whether or not people can tell the difference in the system that was used to generate the artwork, whether or not it's Dolly, your system, or some of the other literature review?
So whether people can tell it was done by like
Which system actually output? Have there been studies just given an output for a participant to be able to correctly determine which approach was used, whether or not it was a hand-painted robot or just a pixel generation system?
I see, that's an interesting study. So when someone is recognized as an artist, there is a theory you have to have a style. So recognizable style. So right now, FRIDA is kind of taking styles from existing artwork. So, I mean, we see emerging style like on its own. So probably I can recognize it's done by FRIDA, but it's subtle. So, but we haven't done any like formal study on that. But that's interesting.
Hey, great. So let's thank the speaker.
Thanks. Thank you.